Welcome back to the Deep Dive. Our mission here is to take that dense stack of sources you've shared, the white papers, the market forecasts, all those R&D reports, and really extract the core knowledge. We want to give you a serious shortcut to being well-informed. Today, we're wading into a subject that it really defines the entire global energy transition. We're talking about storage.
We are, and for decades, one single chemical element has completely reigned supreme: lithium.
Absolutely. Lithium-ion technology. I mean, the Li-ion cells are in everything, right? From your wristwatch to the highest performance electric vehicles, it's really provided the blueprint for all of modern portable energy.
It absolutely has. But that long reign, well, it's exposed some pretty serious vulnerabilities. We're talking about incredibly volatile prices, supply chain concentration risks that frankly worry every government.
Oh, for sure.
And a significant environmental footprint that's linked to some really intensive lithium mining and processing.
And those deep-seated concerns are exactly what has fueled this particular deep dive. We are investigating the most compelling near-term challenger to that lithium-ion dominance, and that is the sodium-ion battery, which people have commonly, and I'd say affectionately dubbed the salt battery.
Right.
So the core question we are trying to answer today, for you, the learner, is pretty simple. Is this salt revolution real? I mean, does sodium offer a true, viable alternative that can fundamentally reshape the energy market and maybe even break lithium's current global chokehold?
Well, our mission today is to go beyond just the marketing hype. We really need to unpack the current status of near-ion technology. We have to define the different chemistries at play because there are a few.
Right, it's not just one thing.
Exactly. Then we need to rigorously assess its real-world performance metrics against the lithium incumbent and detail the global race for commercialization. We're especially interested in how this technology is positioned for those really critical, high-volume applications like grid storage and, entry-level electric vehicles.
Okay, so to set the scale right away, we have to talk about abundance, because this is the foundational argument that really drives the entire conversation. We're swapping a resource that's measured in, parts per million, for one that is almost universally available. Sodium is the sixth most abundant element in the Earth's crust. It is at least 1,000 times more readily available than lithium.
1,000 times.
That's not a marginal difference. That is a fundamental re-engineering of the entire supply chain potential.
And here's why that 1,000x figure is so crucial, geopolitically speaking. Sodium is sourced globally from incredibly ubiquitous resources. You should be thinking vast salt deposits, like the ones that make up the Green River Basin in the United States. Or just seawater.
You're right, so it's everywhere.
It's everywhere. That availability fundamentally removes the geographical constraints, the mining scarcity, and the supply chain volatility that are just, inextricably tied to lithium production. Lithium often relies on these complex, geographically concentrated brines or hard rock mining operations.
So we are talking about swapping a rare, concentrated, and frankly strategically controlled resource for one that is nearly limitless and globally diversified.
That's the promise.
Okay, let's unpack this core value proposition then. Let's move from just abundance to the practical implications, which are cost and safety. Because when you compare the raw battery materials, the difference isn't just large, it's exponential. It completely changes the economic feasibility of massive projects.
Absolutely. The material availability contrast is just stark, and it directly influences pricing. As you said, sodium makes up about 2.6% of the Earth's crust. Lithium, for comparison, barely registers at 0.0017%.
Wow.
So when we look at the raw materials that you need to manufacture the positive electrode, the cathode, the cost differential is staggering. Battery-grade lithium carbonate currently ranges from, $10,000 to $11,000 per metric ton?
And that price has been all over the place in the last few years, just wild swings.
Wildly volatile, exactly. So now compare that. The same foundational material for a sodium battery, which is battery-grade sodium carbonate.
You mean soda ash?
Just soda ash, yeah. It's currently priced around $600 to $650 per metric ton.
Okay, so that's an order of magnitude difference right there.
Yeah.
And importantly, sodium batteries also often avoid some of those other expensive and kind of contentious materials like cobalt and nickel, which drives the input cost down even further.
Precisely. And this differential, it translates directly into the final product cost. Industry projections are aggressive, suggesting that Nanion is poised to achieve a significantly lower production cost baseline. We're talking potentially $50 per kilowatt hour, compared to an average of maybe $70 for Li-ion in the near term.
$50.
But here's the eye-opening figure. Influential energy agencies like IRENA, They suggest that with continued scale-up and R&D refinement, nanoline costs could drop even further, potentially hitting $40 per kilowatt hour.
Okay, so if the industry can reliably hit $40 a kilowatt hour, what does that actually do to the market? I mean, what does that unlock?
Well, it changes the entire economic feasibility of large-scale electrification and grid stabilization projects. When batteries fall below a certain threshold, let's say $50 per kilowatt hour, they become economically viable for applications where price is absolutely paramount.
Like long-duration energy storage or utility-scale power projects?
Exactly. Even if they have a slightly lower energy density than lithium, this kind of dramatic cost reduction means that grid operators could deploy energy storage that is significantly cheaper than, say, building new gas peaker plants to handle peak demand.
Okay, so moving beyond the pocketbook for a minute, let's talk about the environment and ethics. Because our sources suggest sodium batteries carry a really powerful sustainability edge.
They certainly do. The entire sodium supply chain, it relies on a far less invasive and destructive process compared to conventional lithium mining. Lithium extraction, particularly from brines in very arid regions, has been heavily criticized for its intensive water use.
Right. It strains local resources.
It does, and it has a pretty significant associated ecological footprint. Sodium sourcing, on the other hand, which often comes from existing salt operations or simply purifying soda ash, is intrinsically less damaging.
And what about the back end? The end-of-life management seems a lot simpler, too.
It is, because the reliance on less toxic and more abundant base materials like common iron or manganese oxides in the cathode, it makes the final batteries inherently easier and less expensive to recycle.
So even though the low commodity value of the sodium itself means the economic incentive for recycling isn't as high as with, high-value lithium or nickel.
Right, that's a key distinction, but the life cycle from the mine or the salt flat all the way to the grid is just inherently cleaner.
Okay, and finally, safety. We've all seen the headlines about thermal runaways and battery fires associated with lithium-ion cells, especially in EVs. How does the salt battery stack up here, particularly for these massive grid installations?
Lithium-ion batteries are generally regarded as much, much safer, and this is mainly due to their increased thermal stability. They use materials and chemistries that just have a higher tolerance for heat and for abuse before thermal runaway is initiated.
So they just don't overheat as easily.
They simply don't overheat as easily as many conventional lithium chemistries, and this significantly reduces the risk of that cascade failure that leads to a fire. And this isn't just a passive benefit. Active research and development are focusing on designs that are inherently fire resistant.
So what does that enhanced thermal stability look like from a material science perspective? What are they actually doing?
Well, it involves leveraging specific material characteristics. For example, some developers are working on using what they call cation anion regulation and flame retardant electrolytes. This basically means slowing down the combustion process if high temperatures are reached. But what's even more compelling is the work being done in aqueous sodium-ion systems. These utilize non-flammable aqueous electrolytes entirely, meaning the liquid inside the battery is water-based and literally cannot burn.
That's a huge deal.
It is. This inherent safety factor simplifies the overall battery management systems and significantly broadens the range of safe deployment, which is, a massive selling point for energy storage systems where reliability and safety within crowded urban areas are paramount.
All right, this is where it gets really interesting, where we need to slow down a little to ensure clarity for you, the listener. We have to clarify that when we talk about sodium batteries, we're not just discussing a single product or a single chemistry.
That's a crucial analytical distinction, yeah.
It's an umbrella term. It covers three main categories, and each one has a distinct maturity level, different operating temperatures, and their own ideal applications. We have to segment the market beyond just the ambient temperature sodium-ion battery, or NiB. We need to know which flavor we're talking about.
Okay, so let's start with molten sodium batteries. These are the true pioneers of this entire field. The research on these traces back over 50 years to the late 1960s. These are the workhorses of early utility storage.
And these are the high-temperature systems, right? The ones that feel a little bit removed from the lithium paradigm we all know.
Exactly. They typically operate at very elevated temperatures, often near 300 degrees Celsius. They have to operate at that temperature to keep the sodium anode molten and to ensure the electrolyte, which is usually a ceramic solid-state separator, remains highly conductive.
And there are two main types.
There are. The two primary established types here are sodium sulfur, or NOS, and sodium metal halide, or NMH. That last one is often referred to by the trade name zebra batteries, which use chemistries like sodium nickel chloride.
Okay, so given that they require all this complex temperature management, why are they still deployed? Why not just wait for the room temperature versions to catch up?
Because they are established, they are proven, and they are highly reliable for massive long-duration projects. These are not futuristic concepts. These are mature technology readiness level 9 systems.
Wow.
The Japanese company NGK, for example, has commercialized NOS batteries and has deployed over 720 megawatts and 4.9 gigawatt hours of storage globally for grid solutions. That includes a massive 108 megawatt, 648 megawatt hour system in Abu Dhabi for load leveling and renewable integration.
So these are real working systems at
A
scale.
huge scale. And on the NAMH side, the Swiss company FC Sonic has deployed over 500 megawatt hours for various critical infrastructure applications. Think telecommunications backup, railways, and even specialized vehicle applications. Their deployment history, despite the high temperature, proves that sodium is viable at utility scale today.
Okay, so let's move forward into the technology that is actively trying to take market share from Li-ion. These are the ambient temperature sodium-ion batteries, or NIBs, the ones that operate near room temperature and chemically mimic what we already know.
Exactly. The electrochemistry here is directly analogous to lithium-ion. We're just shuttling sodium ions back and forth between a cathode and an anode, which is generally graphite or hard carbon.
And what are the cathodes made of?
The systems often utilize things like transition metal layered oxides or TMLO, polyanions, or Prussian blue analogs, PBAs. But the key material benefit, which links right back to our cost discussion, is that NAIBs generally do not rely on expensive cobalt or nickel.
Okay.
And, crucially, they don't require copper negative electrode current collectors.
Why is avoiding the copper current collector such a big deal? That sounds like a small detail.
It's a cost and complexity issue. In Li-ion batteries, you need a copper foil collector on the anode side. But with sodium, you can successfully plate it onto much cheaper aluminum foil, which is about a third of the cost and far easier to source. This is another small but significant factor that drives down the overall production expense of the NAIB.
Interesting. So within this ambient NIB category, we find a fascinating subset, aqueous neon batteries. Tell us more about those Prussian blue analog systems developed by companies like Natron Energy.
Right. This is a perfect example of designing a chemistry for a very specific use case. Natron Energy, which is based in the US, has focused on using non-flammable aqueous electrolytes, so water-based, combined with Prussian blue analogs, or PBAs, as the cathode materials.
TBAs. Can you just quickly define what those are?
Sure. They're essentially complex iron cyanide salts, but they have a highly stable, very rigid cubic crystal structure. And this structure is fantastic for rapid ion movement.
So what does that mean for performance? What's the trade-off?
It means they are ideal for high-power, short-duration applications where rapid charging and discharging are essential, but the energy density, the mass-to-power ratio, is secondary.
So you're thinking data centers, grid ancillary services, or EV fast charging stations.
Exactly. The trade-off is very clear. They offer a relatively low energy density, around 70 watt-hours per kilogram, which is similar to advanced lead acid, but the cycle life is just phenomenal. Natron systems are rated for at least 50,000 cycles.
50,000. That is fascinating. The fact that an ambient temperature sodium battery is achieving a 50,000 cycle life means we need to fundamentally redefine how we think about energy longevity. That's transformative for something like a data center.
It absolutely is. When you are running a data center backup system or performing utility peak shaving, that 50,000 cycle lifespan is far more valuable than maximizing the range of a vehicle. A typical Li-ion battery might have a maximum of 10,000 cycles, often much less. Natron's approach capitalizes on sodium's strength and power density and stability, and it sacrifices energy density for extreme durability and safety.
Okay, and finally, let's turn to the horizon. Solid-state sodium batteries, or SSSDs. This is the next generation, and it seems to be borrowing the ambitious concepts from the solid-state lithium race.
It's a crucial parallel effort. The core concept is to replace that volatile, flammable liquid electrolyte with a solid-state electrolyte, an SSE. This dramatically improves safety, and, at least theoretically, it opens the door to using metal sodium anodes, which should significantly boost energy density.
And you'd be borrowing the high-capacity cathode chemistries from the ambient NIBs we just talked about.
Exactly. In this solid design, it specifically addresses the two biggest safety and longevity issues, flammable liquids and dendrite growth, which is what causes internal short circuits.
Right, those little metal spikes.
Precisely. For instance, engineers at the University of Queensland developed a solid, plastic-like core that is non-flammable and acts as a physical barrier. This eliminates the liquid electrolyte, and it prevents the growth of those metallic sodium spikes, or dendrites.
And how did it perform?
In lab tests, this design showed remarkable consistency. It promised over 5,000 hours of useful life, even after 1,000 charge-discharge cycles at high temperatures. That's a really strong sign that solid-state, non-flammable sodium could be a disruptive technology, if it can be scaled.
So what's the current status of solid-state sodium? Is it close?
It's still largely in the development phase. It's facing the same critical manufacturing challenge as solid-state lithium, which is how do you maintain stable, low-resistance dynamic interfaces between two solid materials, the electrode and the electrolyte, across various operating temperatures.
It's tough to get two solids to connect perfectly as the battery expands and contracts.
It's very tough. However, companies like Adena Power have successfully demonstrated a 1 kilowatt-hour SSSB module, and their ambitious target is to bring the cost down to under $50 per kilowatt hour for systems designed for 6 to 18 hours of discharge duration. So they're specifically targeting that long duration grid market. This really shows the aggressive, high stakes nature of this third chemistry pathway.
Now we have to talk about the inevitable trade-off. Because if these salt batteries are so cheap, so abundant, and so safe, why isn't every EV running on them right now? And the answer comes down to a fundamental wall built by physics: density versus duration. This is the major hurdle, particularly for high-performance vehicles.
This is the physics constraint that you just cannot engineer away entirely. The sodium ion is approximately 3 times heavier than a lithium ion.
3 times?
3 times. That difference in mass inherently reduces the gravimetric energy density of the battery cell. What that means is, for a given amount of power, the sodium pack will weigh more and take up more volume than the equivalent lithium pack.
Okay, so let's quantify that inherent difference, and then maybe we can layer in the chemistry constraint on top of it.
Sure. Standard high-performance Li-ion batteries, think the ones that power a long-range Tesla, they can achieve energy densities ranging from 100 up to 300 watt-hours per kilogram. Neon technology, on the other hand, currently falls lower, typically in the 100 to 160 torr/kilogram range.
So if you need, say, 75 kilowatt hours of power for your EV, the Neon pack is going to be significantly larger and heavier, and that's going to impact efficiency and the whole vehicle design.
Exactly. And that density issue is compounded by the chemical reality of redox potential.
Explain the redox potential constraint for us clearly. What does that mean?
Well, redox potential relates to the voltage delivered. Sodium's potential, its ability to gain or lose electrons efficiently, is naturally 10% to 25% lower than lithium's. Chemically, this means that even if you move the same number of ions across the electrolyte, the sodium system supplies less voltage and therefore less energy per ion that successfully reaches the cathode.
And that's a fundamental thermodynamic constraint. Developers can't change the laws of physics.
Right. They have to use advanced material science to try and mitigate its effect, but they can't eliminate it.
The narrative, however, seems to be changing quickly. While physics is difficult, engineering innovation is relentless. We're already seeing advancements that directly challenge this perception of perpetually low density. And this brings us back to the biggest player in the game, CATL.
It does. CATL, Contemporary Amperex Technology Company Limited, announced a massive breakthrough in their latest generation of neon batteries. They claim they achieved an energy density of 175 watt-hours per kilogram.
Okay, 175. That figure is highly significant because it makes neon density competitive with many mass-market lithium iron phosphate batteries, LFP batteries, which are already widely used in affordable EVs and stationary storage.
That's the key comparison. Hitting 175 kilogram is the milestone that pushes neon out of the niche category and squarely into the mass market category.
And what does CATL claim this density enables in a car?
They claim this density is sufficient to enable over 500 kilometers. That's roughly 310 miles of pure electric driving range in a mid-size sedan. And we are already seeing this manifest in commercial applications. The IDO M6, for example, is an EV powered by a next-gen sodium new energy battery.
So think about this symbolic importance here. We are talking about a major mass-market EV company moving its latest offering using salt batteries, not lithium.
That is the true signal that the transition from a lab curiosity to a commercial reality has really begun.
So the density gap is closing, but Neon also excels in areas where Lion has historically struggled, things like thermal performance and charging speed. These are key advantages for specific markets.
Mhm.
Let's start with cold weather, which is a huge headache for EV owners in winter climates.
It is, and Naon batteries provide incredibly reliable storage and performance at ultra-low temperatures, better than many comparable Li-ion chemistries. This is a massive factor for adoption in places like northern China, Siberia, or the Canadian prairies.
Yeah.
CATL, for instance, unveiled a sodium battery that is capable of operating at temperatures as low as -40 degrees Celsius. This is crucial for expanding new energy vehicle adoption in cold climate regions and, ensuring range predictability when the temperature drops. It addresses a major consumer complaint about current EV technology.
And speed. Everyone wants to charge faster.
Well, this is where Neon has a major inherent structural advantage. Because the sodium ion is larger, developers often use materials with larger channels in their crystal structure like hard carbon to accommodate the ion, and this larger channel size allows for faster movement of ions into and out of the electrodes.
That means faster charging.
Much faster. Indian researchers, leveraging this principle, developed a super-fast charging Neon battery that still maintained over 3,000 cycles. Heine Battery unveiled a solution for commercial vehicles that can achieve a full charge in just 25 minutes.
Wow.
And even more aggressively, a prototype from KAIST in Korea was shown to recharge in seconds. A true supercapacitor-like performance.
That kind of high-rate capability is essential for heavy-duty commercial applications, robotics, drones, and high-power applications like data center backup, where the requirement is intense power for just a short burst. It's a key market differentiator.
It is. And finally, let's consider cycle life. How many times a battery can be charged and discharged before significant degradation? Li-ion, depending on the chemistry, whether it's NMC or LFP, typically achieves between 8,000 and 10,000 cycles over its operational life. Where does standard Neon sit?
Generally, current Neon batteries sit around 5,000 cycles, which kind of reflect their current lower maturity level compared to Li-ion.
Right. However, we've already seen specialized Neon chemistries push this boundary significantly. As we mentioned earlier with Natron's aqueous PBA systems, they are hitting 50,000 cycles.
Which is just incredible.
It is. Furthermore, companies like Inlight Energy are claiming their iron-sodium battery technology can achieve up to 7,000 cycles and a lifespan of 20 years. That cycle life directly rivals existing large-scale Li-ion systems, like the Tesla Megapack, and positions iron-sodium as a very powerful contender for long-duration ESS applications. The key takeaway is that for ESS, Neon is already highly competitive on durability and stability.
So these performance trade-offs, they clearly signal that Neon isn't trying to fight lithium-ion head-to-head on its home turf, which is high-performance mobility. It's strategically carving out entirely new territory based on cost, safety, and longevity. And the primary application focus is loud and clear. Grid storage, energy storage systems, or ESS.
Absolutely. For stationary storage, the constraints change dramatically. Weight and density are far less critical than cost, safety, and longevity. If a battery is 50% heavier but 30% cheaper, the heavier pack wins the utility contract every single time.
Right, because land and installation costs are fixed regardless of the chemistry.
Exactly, and market forecasts reflect this strategic positioning. It's predicted that a massive 70% of Neon batteries will be used for energy storage by 2026.
And we've seen these announcements coming fast and furious. What are we seeing in terms of specific, large-scale, real-world ESS deployments today that illustrate the scale we're talking about?
Well, the deployment pace is accelerating rapidly into the multi-gigawatt-hour scale. For instance, Peak Energy is set to deliver 4.75 gigawatt-hours of sodium-ion systems to Jupiter Power for U.S. grid storage. That's a significant commitment.
4.75 gigawatt-hours.
We also have confirmation of what's been called the world's largest single Neon storage project, which is powered by Sinning Electric in China.
Help us visualize that Sinning Electric project capacity. What does it actually do?
The initial deployment of the Sinning project is reportedly around 100 megawatt-hours, and that's capable of powering approximately 12,000 homes. So this isn't just a pilot, it's a full commitment to use this technology for load shifting and stabilizing a regional grid. It validates its readiness.
And what about for businesses?
Well, Biduat, another key player, unveiled commercial Neon ESS, specifically targeting commercial and industrial use. So think of factories, hospitals, and large office buildings looking to offset peak energy charges. The market is aggressively moving from megawatt-hour pilots to gigawatt-scale deployment.
So while grid storage is clearly the main target, NAN is also making inroads into the mobility sector, specifically targeting that affordable and smaller vehicle niche where cost sensitivity is paramount.
That's the estimated 18% of the market forecast to be allocated to EVs. The debut of the JC Group's Yue, which has backing from Volkswagen as the world's first sodium-ion powered EV, that's incredibly important. But the real sweet spot for Neon is elsewhere.
Right.
The technology is perfectly suited for cheaper, smaller forms of electrification where cost savings matter most. Think of the millions of e-bikes and e-scooters in Asia, microcars used for urban transit, and crucial industrial vehicles like forklifts and material handling equipment.
And there's a massive opportunity in replacing an old technology we haven't even talked about yet. Lead-acid batteries.
Absolutely. Lead-acid batteries, which are still ubiquitous in cars, data center backup, and industrial equipment, are heavy, they're toxic, and they have very low performance. Unigrid, for example, is specifically introducing 12-volt neon batteries to replace traditional lead-acid technology.
So swapping out lead for salt.
Exactly. It offers a performance increase, it removes toxic material, and it provides a much longer lifespan, all while maintaining a competitive price point. This is a massive underserved market that Neon is perfectly suited to dominate.
So, if the technology is ready for gigawatt scale, what does the global manufacturing race look like geopolitically? Who is truly driving this push?
Currently, China is the undisputed leader. They recognize the strategic importance of this alternative chemistry very early on and have just dominated innovation, mass production scale-up, and standardization. CATL, which is already the world's largest battery maker, is spearheading this with their Nextra line.
And their influence is so profound that their Neon battery was the first in the world to achieve compliance with China's really rigorous EV safety standard.
That's right, the GB 38031-2025 standard. Achieving safety compliance this early is a huge signal of commercial readiness, and it establishes a benchmark for the rest of the world to follow.
So that sounds like a decisive and powerful head start for Asia. You have major players like CATL, BYD, Hina, S-Volt. All of them are projecting or already beginning GW scale production. What is the counter strategy from the U.S. and Europe?
U.S. efforts are strongly focused on niche, high-power applications and, critically, on building domestic capacity to control the supply chain we discussed earlier. Nature and Energy, for example, is actively manufacturing its aqueous PBA systems specifically for high-power demands like data center backup, which provides immense margins and validates the technology domestically.
And they are backing this with a massive, what was it, a $1.4 billion investment?
A $1.4 billion investment in a North Carolina gigafactory, explicitly aiming to create a self-sufficient, non-Chinese dependent supply chain. Peak Energy is also establishing a Neon battery center in Colorado, supported by significant funding.
And Europe. They must be highly motivated to find non-Chinese, non-lithium dependent sources to support their own green energy transition.
Oh, European innovation is strong. You have Swedish startup Altris, France's Timat Energy, and major players like Northvolt all pushing ambitious European sodium initiatives. The market growth projections are aggressive because of this global commitment.
Right.
The entire global neon market is projected to grow exponentially. Some forecasts are predicting a 21.2% compound annual growth rate by 2030, reaching a market value of $1.84 billion.
And that's just the start.
It is. Current projections for manufacturing capacity from all these players suggest a massive industry boom is not just coming, but is already underway. Experts like Wood Mackenzie suggest we could see 40 gigawatt-hours of NAIBs alone by 2030, with the potential for 100 gigawatt-hours if commercialization successes continue at this pace.
Okay, now we get into the nitty-gritty, the research pathways and strategic imperatives. To truly understand the future of Neon, we have to look at how governments and major research institutions are directing serious investment. And that starts with the U.S. Department of Energy's ambitious long-duration storage shot initiative.
Right. The DOE's goal, framed under the Storage Innovations 2030 initiative, is a genuine moonshot. They are aiming for a 90% cost reduction for technologies that can provide 10 hours or longer of energy storage duration.
90%.
90. The target is a levelized cost of storage, or LCOS, of 5 cents per kilowatt hour. This is the benchmark for truly transforming the grid. If storage is that cheap, it can easily dispatch renewables even on days with no sun or wind.
That is an incredibly aggressive target. So, where did the baseline LCOS estimate for NAIBs sit just a few years ago?
The 2021 baseline LCOS estimate for NAIBs was about 55 cents per kilowatt hour.
55 cents. So the path to 5 cents is not just steep. It requires fundamental, transformative breakthroughs in materials science and manufacturing scale.
Absolutely. The DOE recognized this and commissioned extensive analysis involving subject matter experts to map out the innovation required specifically for NAIBs that use transition metal layered oxides, the most common high-energy chemistry.
And what did those simulations show about the feasibility and, the timelines to bridge that massive gap?
The simulation findings were highly illuminating. They found that the very top R&D portfolios, so ones that combine multiple successful innovations, could reduce the LCOS by between 49% and 59%. That would bring the cost down to a range of 23 to 28 cents per kilowatt hour.
So that's a massive step. It validates the technology's potential, but critically, it does not hit the ultimate 5-cent target.
Exactly. It confirms that NIABs are still an immature commercial technology that requires significant foundational work.
And what do they project for the investment required? Because that gives us a measure of the strategic commitment.
Critically, achieving this level of reduction to that 23 cent per kilowatt hour range is estimated to take between 9 to 13 years and require industry expenditure between $125 million and $362 million.
Okay, so this is a crucial data point for you, the learner. The cost advantage is potential. It's contingent on overcoming nearly a decade of heavy investment in R&D hurdles. It's not a guaranteed present-day reality for all applications.
That's a very important caveat.
So if we look at the R&D innovation roadmap, where are those fundamental breakthroughs most needed, according to the DOE's experts? Where does the money have to go?
The emphasis is overwhelmingly on materials and chemistry innovation. The single highest priority innovations, which were represented in the top-performing portfolios, are cathode development.
Okay.
So focusing on creating materials that operate at a higher voltage without degrading rapidly, and electrolyte development. That includes pursuing both solid-state options and non-flammable organic solvents. These two areas accounted for about half of the expert responses regarding required innovation.
So if we can get a higher voltage and a safer solvent, we solve most of the current limitations.
That's a huge part of it. The experts also heavily highlighted improving the cathode electrolyte interface stability, the CEI. You can think of the CEI as the point where the solid material meets the liquid. If that interface breaks down due to chemical side reactions during cycling, it's like a car engine seizing up. It causes rapid capacity loss. So R&D needs to find ways to keep that interface stable for thousands of cycles.
And what else?
There's also a focus on in-operations materials science research, so understanding exactly why existing cathode materials degrade rapidly during cycling using advanced imaging and diagnostics. And then there's the really radical approach we touched on, anode-less battery development.
That concept still sounds like science fiction to me. Anode-less anode.
Essentially, yes. It eliminates the anode entirely. You use only the cathode and a simple current collector, and you allow the sodium to plate directly onto that current collector during charging. This path requires novel materials, but if it's successful, it promises dramatically simplified cell construction and much higher energy density.
Because you're removing a heavy, bulky component from the cell design.
You are. It would immediately help close that density gap with lithium.
So beyond the chemistry, the R&D also requires supporting the whole ecosystem for commercialization. Otherwise, the labs just churn out breakthroughs that the market can't actually implement.
Absolutely. The R&D agenda explicitly requires support for volume and mass production planning for grid-scale deployment. It requires developing advanced controllers to improve cycle life, optimizing battery management systems specific to sodium, and crucially, large-scale deployment efforts like grid-scale pilot testing to de-risk the technology for cautious utility stakeholders.
Let's shift back to geopolitics for a moment, which is where the U.S. has a potentially unique strategic opportunity, given its domestic reserves of the raw material.
This is a major non-technical strategic lever for energy independence. The United States sits on the world's largest natural repository of soda ash. That is, sodium carbonate accounting for a staggering 93% of known global reserves.
93%.
A total of 24.7 million tons. This is in stark contrast to the U.S. position regarding lithium mineral reserves, which are relatively poor and geographically constrained. This huge domestic soda ash supply provides a key opportunity for the U.S. to establish and maintain control over the emerging neon supply chain. It offers a clear pathway toward energy independence that bypasses the current manufacturing and supply constraints that are primarily controlled by China.
What stands out to me is how the DOE study also analyzed the non-technical hurdles. It identified where market forces or policy are slowing things down, even when the technology is ready.
Yes, the system itself presents significant challenges. The most critical non-technical hurdle they identified is supply chain immaturity. This is a self-reinforcing commercial cycle, a classic chicken and egg problem.
Right.
Because there is currently limited battery manufacturing volume, material suppliers are not incentivized to invest the vast capital required to build larger volume supply chains for sodium battery grade precursors. This inertia keeps costs high and limits battery manufacturing, which completes the negative feedback loop.
So you need some kind of public intervention to break that cycle.
Exactly. Something similar to the strategic model seen in Europe and Asia may be necessary to break this inertia and fund the foundational supply chain buildup.
And if the U.S. wants to compete, they also need to address policy and standards, which are inherently biased toward the incumbent, lithium.
That's a huge point. Currently, the entire ecosystem, including safety policies, national standards, and certification processes, is heavily focused on lithium technology. Lithium batteries, which have different optimal use cases, operating windows, and safety profiles, are essentially forced to fit into an inappropriate regulatory framework.
So we need specific codes and standards for sodium.
There is an urgent need for NAS-specific codes, standards, and validation, particularly around integration with grid power electronics and specialized material handling requirements, especially for those molten sodium systems we discussed earlier.
And finally, the disposition of the battery's end-of-life management. Since sodium materials are so abundant and low cost, does that create a challenge for recycling economically?
It does. While the materials are less toxic, that low cost limits their recycling value, decreases the economic incentive for their disposition compared to highly valuable lithium, nickel, or cobalt scrap. Furthermore, for the molten sodium chemistries, the pioneers we talked about, safely handling metallic sodium during battery disposal requires specialized and expensive expertise and infrastructure that is not yet well established in the US or Europe.
So if we want a truly sustainable loop, we need to proactively fund education for regulators and establish clear, safe disposition pathways now.
Right, not after millions of batteries have already been deployed.
So let's synthesize all these findings. The breakthroughs in density, the fundamental physics constraints, the immense cost advantages, and the aggressive global race for deployment. Where does the sodium battery actually fit into the future energy landscape?
The core finding is clear, and it must guide our strategic thinking. Lithium is highly unlikely to replace lithium-ion entirely for high-performance electric vehicles. That's because of those physics-based density limitations. Lithium will almost certainly remain the king of maximum range and lightweight mobility.
However,
lithium is fundamentally poised to be a dominant complementary force in two critical massive markets: large-scale energy storage, or ESS, and affordable entry-level mobility. When weight and space are not the limiting factors, the cost, the abundance, and the safety of salt batteries make the incumbent lithium chemistries, well, economically irrational for those applications.
so that sounds like a future where we leverage the strengths of both salt for stability and price, and stone, which is lithium, for density, which is exactly what we're seeing in recent R&D with these hybrid pack designs.
Precisely. CATL, never one to let a competitive advantage slip, is already developing what they call an AB battery pack solution. This pack combines high-energy lithium cells with high-power, low-cost nanion cells within one integrated system.
So they might use nano for stable, low-cost daily capacity.
Right, for your daily commute, and then have the LAN for those moments of high-power acceleration or for maximizing the total range on a long trip. This kind of hybrid architecture is likely to define the transition period for mass-market EVs.
This whole conversation really boils down to salt versus stone. It's abundance versus rarity, and it's about geopolitical control. The U.S. controls 93% of the global soda ash reserves, representing a massive potential source for the lithium supply chain, and it offers a path to domestic energy manufacturing independence.
And that is contrasted starkly with the fact that China controls over 90% of the global supply chain for graphite, a critical material used in lithium anodes, and absolutely dominates lithium processing.
Which brings us to our final provocative thought for you to mull over. If we accept this future defined by two parallel, distinct battery supply chains, one saltwater, one lithium, how might this fundamental split reshape global economic power? And how might it accelerate the path to a truly diversified and sustainable energy future?
Does controlling the abundant foundational supply chain for sodium offer a more sustainable, long-term strategic advantage than controlling the current high-performance but resource-constrained supply chain for lithium?
And that is a question that the next decade of investment policy and R&D will ultimately answer.